today. This meeting is being recorded. Our speaker today is Dr. Bijan Pashaie, and Dr. Pashaie brings over 20 years teaching experience and holds a PhD. In his field, he has researched plasma technology that's resulted in 25 reviewed journal and conference publications. As a program coordinator for engineering technology and skilled trades, he oversees a diverse range of courses. His teaching portfolio includes Introduction to Unmanned Aircraft Systems and its relation to GIS, college mathematics, engineering physics, circuit theory, and electronic communications. In addition to these subjects, Dr. Pashaie instructs classes for the Precision Machining Technology program and teaches dual-enrolled high school students. He's also involved in teaching robotics. While primarily based at Flow Valley, Dr. Pashaie actively participates in the Engineers Club of St. Louis Community College. He's a senior member of the Institute of Electrical and Electronics Engineers. Welcome, Dr. Pashaie.
Thank you. Thank you, John. I really appreciate being here. It's a pleasure. I'd like to thank everyone that made this a possibility, from Ms. Galanis to Brad, who's saving us here, and everyone in attendance, in addition to the library system as a whole, and then also also the Flow Valley campus that allowed me to take the time to present this and prepare. Thank you very much. So let's get going then on the, first I'm going to show you maybe a couple of things, and then we get going with the actual presentation. Hopefully it'll be about 40 minutes, 45 minutes. Then I got to go teach, and then after that, run the Engineers Club at Merrimack. Yeah, I hope you enjoy, and it is hope that it'll basically induce some interest and excitement, and in all that are present. Yeah, thank you. So here I have. I'm going to show you just a few. The title of the presentation was selected as Our Sun and How it Relates to Our Lives, which is so critical. I brought the sun basically is a big gaseous plasma. I brought a couple of examples for you, and hopefully to get it going, to see the perspective. And please understand, each one of these 35 slides or so could theoretically be a lifetime of work. So I'd like to thank everyone who has spent their lifetime or their career doing just that. Yeah, sometimes behind the scenes. So here we have first something that you may have seen before. This is popular in popular culture called a plasma ball, where it's, let me see if I can make sure you can see it. There we go. You can kind of see the plasma a little bit. I try to cover the backside so you can see the streamers. This is a streamer-dominated plasma. The way these actually work is that, let me touch the top, and then you see it. Let me try to show you what the top is, because it tends to actually show you the current that reaches where my finger is. I try to use one finger. It becomes more intense as a result, because one important factor besides the slides that are coming up is that how can I create such a plasma? One is by heating. So my hand right now is actually heating the top of this glass, and the further I hold, the warm. Eventually, my finger is going to hurt a bit. I'm not getting actually zapped or anything because of the glass, because the plasma is the electrical conductor. However, the glass, generally speaking, is not. So that's why I'm able to push my hand here and just hold it there for a while. The way now I'm going to let go, and as you see, I try to hold it. So it tries to actually go in all directions, as you see here. That is because it cannot see a difference actually between that. And that is the electrical side of things. It sees a positive in the middle and a negative on the outside. And as a result, the electrons get emitted from either the one side or the other side until they reach the opposite. I can take a penny right now and actually hold it here, not with my hand, but with maybe a pair of pliers, and actually it will arc outside of this glass because there's actually energy here, even though, and I can induce a current out of voltage. That's kind of cool. The way they make these is, first, this is battery operated. They actually increase the voltage on the inside, then they multiply the frequency of it. So this is actually a high frequency electrode in the center, as you can see, the center of it. What's interesting is, as I'm going to talk about the sheaths or the Debye lengths of a plasma in a few minutes. You can see, if you see really close to the center, look just outside of this center high voltage electrode. This actually looks almost like an invisible little umbrella or coat that it surrounds it. And that's really interesting. And so this is basically known. And the streamer is, if I touch it now, you see a bluish looking arc, almost like a minute lightning. And that will continue until it reaches a destination. That is the coolest thing. So you can actually see for yourself a current being created. The reason why it's so easy to do this with 4 AA batteries in this case is because of the fact that the pressure inside this ball is kind of low. So as pressure increases, it takes more energy to actually make it conduct. Whereas in this case, the pressure being low, meaning actually what's inside this ball, the gases inside this ball, which is most likely nitrogen. So it actually is easier. I don't need much, and I can do this job. So please understand that we're going to discuss, there's some very important parameters, 2 of which are density and 1 is temperature. Temperature means that how fast things are moving. Density means how many of them there are. And one more thing is that these are ionized gases. Ionized means that if I shut this off, now it's back to nitrogen again. It'll take a bit, but not long. Now I'm excited, and you see that what used to be nitrogen is now excited nitrogen. And there is an excited gas, so these are ions, which might be positive or might be negative. They're electrons, and then they're positive ions, in addition to possibly more. Sometimes all the gas is ionized, sometimes half is ionized, sometimes a minute amount is ionized. There you go. So they're kind of a runaround of what a plasma actually is. Yeah, people have been studying this activity since the 1950s, and I'm indebted to a lot of individuals in this field. Yeah. So now what I got for you is I got this chair. I got this slightly different type of plasma, which is actually a laser. And this is a nice laser that the cover was removed for academic purposes. And you see, actually, this is a gas laser, helium neon laser, as it is called. And thank you, Brad. And so let me turn that on. You just plug it in, push this button here, and look what happens. Almost like a light bulb. Let me turn it off, and I'm back on again. Well. So here, you got actually a plasma. The purpose of this plasma is different from the other one. It's supposed to be as nicely as uniform as possible so I can actually make it laze. And how do I make it laze? Well, I just basically, it's already lasing. You can see it on my hand, little reddish beam, and I can make it open up a bit further. And there it is. Let me see if you can kind of see it bounce off my hand. There it is. There's the actual laser beam. Now, what makes this for safety, I lock this back up. So as you see here, this portion of it in the middle is actually a plasma, which takes the neon, basically is a helium neon, one excites the other and makes it a plasma, which is located in the center of this little column here. And this is what eventually lasers by introducing the mirrors on both sides, having the right voltage, having the right pressure, having the right gases, and doing it just right. So there you have usually you can't see this because they put it in a metal box for obvious reasons. And so here you have a plasma, which is really just that. Again, it's also a low pressure plasma, but it has to be done just right. Yeah. So I appreciate that. And then now we get into the basic introduction to what we're actually talking about. Here you have the Earth. Here's a moon that's circling around, and this little light bulb here is meant to demonstrate the sun, which is millions and millions of miles away. So this is a bit of a stretch. The sun would actually be much further away, as we're going to see in the slides. Yeah. So as you see here, it actually introduces it makes life essentially possible, provides the light, which provides the agriculture and the plants in photosynthesis, either aerobic or anaerobic, and then also provides the seasons depending on the tilt, and essentially everything. So there's a German saying among the engineers which says that Licht ist Leben, which means that light is life. That's a sort of a tradition among people in the field. Yeah, gets them motivated and what have you. So today we're going to talk about this right here, this little sun, and what is in here, and what as best we can. Please understand, we got about a half an hour or so. I hope I can do it justice during that time. And at any time, if you're interested, right at the end, please ask questions. And if today we can, we make sure we get back to you. Yeah. And so let's get started. And another good news is, among the students who were kind enough to be in attendance today, we're going to, afterwards, after the fact, we're going to raffle a second plasma ball, and somebody will hear from us by Monday. Yeah. So let's stay tuned. Yeah. Hopefully you like it. And I ship you batteries too. All right. So there we go. Now, Brad, if you please, if you can start the PowerPoint, if you could, please. Yeah. Thank you very much. All right. Yes. So, ladies and gentlemen, it's a pleasure to be able to do that. Oh, okay. So we go. I'd like to thank everyone, as I indicated, for being here today. And I'm indebted to the library system. I like to make a point to that. Albert Einstein basically said, oh, okay. All right. So then the first one. So then okay. Yeah, yes, that's fine. Yeah. So Albert Einstein basically was quoted as saying that the only thing that you absolutely have to know is the location of your library, which is that's really cool, because I'm indebted to many librarians over the years, and I like to make a point of that. Yeah. So now we go forward. Right? So here you have that's kind of really nice. Plasma is known as the fourth state of matter. And the surprising thing is that almost 99% of all matter in our known universe is actually plasma. And only 1% is what we see on a daily basis as being gas, liquid, solid. That's it. And so the plasmas are actually the vast majority. As you see here on this picture, the vertical axis is the temperature given in degrees Kelvin, which is really about 273 by about 273.5 degrees compared to Celsius. And then in the bottom, it says the density. You know, it's how much of these ionized particles where electrons have been removed from the outer shell of that particular atom is actually there. And as you see here, they got in the center of it, actually got a neon bulb that you see on the street, downtown, or wherever the case might be. Then you got the corona, which is of so much interest these days, also in the center, just above it. To its right is lightning, a totally different type of plasma. Huge millions of amps of current are basically delivered in a very relatively short amount of time to a short location, to a small location. I wish I knew how to extract that power. I haven't figured that out. That's tough to do. Solar wind, which is of really interest these days, is on just the center left. The aurora, which is the result of the magnetic field created by that, is on the bottom left. And finally, on the top right, you see, and the top right, you see actually fusion, which has been of interest since the 1960s, where people can generate electric power using magnetic fields. There are two types. We discussed mostly the magnetic one today, known as a tokamak. And then you have laser inertial confinement using lasers, which may be for another day. Yeah. So you see, there's a vast variety of plasmas from being very hot, which is usually indicated by the positive particle actually being fast. The electrons are often going fast anyway. So by really cold plasmas is a plasma where you can actually touch. They use it in medicine, they use it for processing of genes or clothes or whatever the case might be. Again, for another day. Yeah. So now we go on forward. And as I said, some things are necessary for a plasma. There have to be some electrons that have been loosened, and then some positive ions as a result. And most of the time, they're actually almost equal in number. Nature likes to be neutral as best it can, but it's very highly conductive. So inside of this, if I could put my finger inside of this, I probably won't feel very good. Now then there's a magnetic field. I forgot to bring my trusty magnet, but what would have happened is this. I turn this on. This right now is what's known as the electric field or force, the force, which is between here and the center. Now, as you see here, I try to cover my hands so you can see these go bad. I try very hard to go in straight lines. They can't exactly, but they try. If I had a magnet here and I put the magnet out here, right adjacent to it as best I could, these charges would actually tend to rotate close to this glass envelope. So these are the three types, three different parameters that can generate a plasma. One, you heat the thing up somehow. Number two, you apply a little voltage to it with a big fat battery and get them excited. Grab the electrons out and let them go. Then number three is you actually create a magnet on the inside and let these electrons, as they're coming out, usually due to the electric field, just and then they rotate and they go. Let me see if this magnet can do the job. I touch it, you can see it. You can see it that right below that magnet that I was kind enough gentleman to loan me. That right here, if you touch just on the glass, right below this magnet, you see these electrons actually not knowing exactly where they want to go. And that is the force, thank you, that is the force due to the magnet. And that's really critical today. All right, some parameters, ladies and gentlemen, not for too long. As in the bottom, you see it says heat, electric, magnetic for creation. Now, we're going to discuss in the sun here for a minute. There's some issues, which must be addressed, some of whom are understood and some of whom are not quite understood. I'll mention that in just 2 minutes. Here we have collisions. Some plasma particles just bounce into each other immediately, like 1 millimeter, like that much after they were generated. Would they get to that? The thereby length must be understood. That's for the details are for another day. But the fact is this: if my finger here is positive, it's going to attract the negatives around it, and it's going to shield it. A lot of them are going to be there. So what's going to happen to the other guys that are out here? That is why this fella by the name of Debye became so famous. Interesting. And remember, this happens everywhere. The density, as you mentioned, how many of these guys are around here. The temperature means that how fast are these guys going around here in all different directions. And for the people who took the beginning physics would be the kinetic energy. Now then here, just something here that is the what's happening here is that the density, just for a few different plasmas, the stars, ooh, that's lots of them, especially on the inside. The laser, the fusion, magnetic fusion, or the tokamak, as we're going to briefly discuss, the laser that you just saw, electrical discharges means that essentially close to this, basically you hold and an arc happens due to the electric field on the line, which I don't do that at home. Then ionosphere is that they basically all around the Earth, and then the interstellar, which means that just everywhere as we know it today. Here's a little core thing about just a cutout of the sun, which is sort of a magic cutout, where you have the sun here blasting the earth at all time and making life possible. And then, oops, but it was. So anyways, so here it is. There was the sun. And what happens here is that we're going to look inside the center of it. As you come out a little further, there's several fundamental layers. The layers of the sun is the inside layers and then the outside layers. 7 major layers. The very inside, the core, where the fusion takes place, as we're going to see in a minute. Then just about that, radiative layer, as in radiation. Closest to here, just inside this yellow envelope, the convective layer. Then we get right on the outside. Right on the outside, you got the chromosphere, you got the photosphere, and you got the corona out here. Which from there, then, all these massive sunspots and emission of these solar winds, which are partially of our interest, which blast the Earth at all time. And from X-rays to gamma rays to electrons to protons, they're all blasting us. What saves us, as we're going to see in future slides today, is the magnetism of Earth itself. The Earth is rotating. By the way, the sun is rotating. The Earth is rotating on the inside. It's got some salty-like metals that are mixed to get together. There's several models for that people try to model that. So it creates this North Pole and South Pole. The North Pole and the South Pole may move around some. So they're weak at the pole, and then they go like this, around and around and around. As the radiation comes from the sun, it blasts this magnetic field and creates some sort of electrical feature, which we call the northern lights, or in fact, they're also on the other side, the southern lights. So if you got my thumb is a current, and here any current, my hand would be, if I go my right hand and close my hand, you see that would be the magnet, the field, the force field due to the magnet, which is magnet being created by these charges, which have either positive or negative. Beautiful, beautiful. For years now, there have been 2 fundamental questions, which we live in exciting times. Because why? Because those 2 questions are slowly being answered, as future slides tell. Number 1, on the very inside, as we're going to see, is really, really hot. Then it cools down, cools down, cools down. Fusion takes place in the core, where helium basically is created due to the fusion of hydrogen atoms, the lightest elements. And it comes out, and it comes out, cools a bit, cools a bit, cools a bit, cools a bit. Then suddenly, it's really kind of cool on the outside. We mentioned that in a bit. Then when it reaches right here, really close to that, suddenly the temperature rises by multitudes of factors to millions of degrees, from thousands of degrees to millions. Why? That's been the question which deserves Nobel Prizes for years past. Then suddenly, out of that, you get these, as you see on this slide, you get these magnetic fields. Remember, magnetic fields always go in a loop? So you see them right there being emitted from the sun. The sun has roughly 11-year cycles, where every so-called more or less 11 years, you get these spots, which are always there, but they become mighty intense. And guess what? We're almost in the 11th year. We're going through it, my best understanding. That is the coolest thing. So the question now is, what makes these guys create this wind where particles, mostly electrons and protons, I mean, they just take off and literally just cook everything that is in their side. What causes that? We know it's hot, but that heat by itself cannot create enough energy to do just that. That is question number 2. Again, a question whose answer deserves a Nobel Prize. Now, here just a little bit of saying the fact that the sun is about 300,000 times as much as heavy as the Earth. How big is it? Roughly about 110 times the size. How dense is it? Well, that's kind of interesting because, on the inside it's really dense, where the fusion gets created and hydrogen basically just are hydrogens of the same charge. So theoretically speaking, these guys are supposed to let go of each other electrically. But if the pressure is so high that literally that overcomes the tendency for them to try to get out of each other, and they can't. And they come closer and closer and closer and closer and closer until literally fusion takes place. And a slight amount of energy is given off. Just that slight amount of energy is enough to essentially heat up our solar system, because the amount of helium created is almost equal to the hydrogen that caused it, but it's a bit off. That's enough. That is enough. And which makes the fusion inside the core of the sun possible. The sun actually rotates. The center of it doesn't rotate like the pole does. The inside doesn't rotate like the outside does. And how can something leave the sun, which is so massive? Roughly speaking, it's got to go like really fast. Now, how? Now, here's the Nobel Prize question. What is causing that little velocity? So, boom, it exits the sun and goes into the space between Earth and sun, as well as other places. The temperature, as we're going to see, actually changes a lot. But think about these 5,000 ranges, which is the surface, more or less, before it gets hot. So what is inside the sun? Tons of stuff, all the way from the 92% hydrogen, which is so plentiful all over the space. Yeah, helium is next in line for about 8%, and then a host of other elements, just about anything you can imagine, is in there in that form. Yeah? Fusion, the details of this fusion are for another day, but look on the left side, you see hydrogen. Look on the right side, you see helium, He. This is what takes place. And look in the middle. Bunch of radiation is coming in and coming out, and that is the energy that is released. Now, well. Certain things have to agree in there. Hydrogen nuclei collide. Temperature is very high, meaning they're going mighty fast. The electrical force, which is trying to separate them, is overcome. As a result, they fuse and form a different atom, helium. And light and heat is most of the energy is released in terms of light and heat. And this takes place in the core of the. Here's just for people who are interested. I try to make it interesting to people in different fields, from astronomy to weather to chemistry to biology. And here's the chemical chart, as you see here. On the top two elements, you see hydrogen on the top left side, and the second lightest, I guess, helium on the top right side. Here we go at different layers of the sun. It's a kind of a cute little graph I found, and cute little graph. It gives distance from the core. The red circle in the middle is the core. Then it goes to radiative zone. That's kind of funny. Actually, the electrons or the ions the electrons that come loose right outside the core, which are being generated, that light and heat being generated right outside the core by the fusion in the core, cannot actually go very far. The density of the radiative zone is very high. So it may only be 1 millimeter before that electron gets absorbed again and makes a neutral one. Then it gets excited again. It moves on. It's like a random walk. It's like go, come, back, forth, go, a bit at a time. And this is thousands of miles. So it may take like 150,000 years before the electron generated here makes another one, 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 a photon, the light, until it reaches the outside of this radiative layer. Amazing. Then it reaches a convective layer. There, suddenly, the density is a little bit less. So these begin to almost be like a fluid, like a mud, almost you could think of like a salt bath. And they begin to move out. They convect like a convection oven in your kitchen or restaurant. They go towards the outside. They cool off. They cool off. They cool off. Suddenly, then they go back in. They literally move. They convect, almost like a convection oven you buy at the store. That's which cooks so uniformly that food, your favorite food. Then suddenly you are now at the edge of the inner portion of the so-called inner element segments of the sun. Then you go now to the photosphere, chromosphere, the so-called transition region, which is very narrow. And finally, on the top of this graph, that mighty corona, which affects our lives on Earth so much. We go to the next one. The temperature required for fusion might be as much as 15 million degrees. About 4 million tons of matter a second might be processed. Then inside that might be 100,000 years. There's debate on that even further for it to reach the outside of the inner. Then it cools down in the convection layer. Then for the photons to exit them. Now it goes in and out. And then now what? Now it becomes very turbulent when it reaches the outside. Let's have a look at that. The photosphere, the chromosphere, and the corona. These are distinct layers which are not the same size and also not the same density and not the same temperature. But there's a tendency as you move to the outside, they kind of cool off a bit until they reach a chromosphere, and then the magnetic field becomes really dominant, which we're going to be discussing. Yeah. Suddenly, outside the transition area, reaching towards the corona, the temperature rises from 8,000 to 5 million. And that now those solar winds are being generated. Let's look at that. You see, these are the famous dark spots on the sun. My last slide, or one of the last slides today, will be about how you can look at the sun. I'd like to emphasize, please, to invest in at least a personal, safe solar telescope, so no damage to your eyes are done. Safety is always number one. Yeah, or go somewhere where one exists. So here we are. These dark spots that are so obvious are actually cooler spots. The temperature is about 1,000 degrees lower than they are in the segments of the outer sun that we see, which is not dark. So again, chances are that magnetic fields are actually being generated there or coming out. Whoa, here they are. Billions of tons of plasma coming out. These are ejected at thousands of kilometers or thousands of miles per second. And they reach Earth very, very easily. The Earth is basically a little bitty dot, which hardly is even recognizable by the sun. If you go on the sun, you barely can see the Earth. So that is why we have to make sure our magnetic field of the Earth, it protects us, because we're just a little bitty dot in essence. As we're going to see also later on in the slides, the center in the United States, which monitors that, is in Boulder, Colorado at the present time, which is part of the basically Space Weather Center. The space weather, you can at any time, you can actually go on the internet, go to this website, and we're going to discuss the pieces of it here. You can actually monitor the space weather, that is, how intense things are, what is going on in space at any time for free right now, 24 hours a day. Here it is. There is the Earth and the Sun, a solar wind, these magic lines which blast mostly protons and electrons. The pinkish purplish lines are the Earth's magnetic field. The bluish lines are the solar wind from the Sun. And the aurora, which is the northern lights, are the green ones on both southern and northern parts. Here is from University of Alberta, the magnetic field involvement. It is estimated that why this is one option right now. Why is the outside suddenly getting so hot and so hot that makes all this possible? It's ejection. And it is likely that these are millions and millions of little bitty magnetic flares getting created, and the sum of which do just that. One of the gentlemen that won a Nobel Prize, a Swedish gentleman by the name of Alfvén, proposed that a few decades ago, and basically what can happen here, known as the Alfvén waves, which are these magnetic fields that go, but these magnetic fields are oscillating, and just that slow in comparison of oscillation is able to generate that force that is a result in what we see today. Here you have another picture of that. The red little arrows that swing around are the variation in the magnetic field that were proposed at the time and gained respect, even though we're not 100% sure. How can we do fusion on Earth? That is, as I said, there's a magnetic confinement, and then there's a laser part of it. We discussed the tokamak, which originally is a Russian term, but it's basically a big old donut, which on the inside, around which they are superconducting magnets and the microwave sources, which heat up the inside of this donut by almost multitudes of factors of the estimated inside temperature of the core of the sun, the inside the Torah. And if you do this right and extract that energy, you can actually generate enough energy to drive, let's say, this electrical needs in the state of Missouri, possibly with only one of them. These are the details of this is for another day. On the left side, you see the hydrogen fusion in our sun. On the right side, you see some of the elements that I use to create the fusion inside these tokamaks, which involve deuterium and tritium, which are isotopes of hydrogen. And look at the energy in the bottom, 14.1 mega electron volts. Whoa, for another day. Now then here, the point I'm trying to make is that many people are involved. We have several in the United States. The Europeans, the southern France is where their main tokamak is located in collaboration with other people. The British have one. The Japanese are very active in addition to other people. Some actually have the money to build it. A lot of people contribute in computer simulations, which is critical in this case, because you have to sustain that plasma and it requires the biggest computers and algorithms to see how we're going to make this. Again, we are lucky to be living at this time because for the first time, the French tokamak, ITER, was able to last week, a couple of weeks ago, be turned on for 22 minutes. That is a landmark. We're not talking milliseconds, we're not talking seconds, we're not talking minutes, we're talking 22. Now, how then do we monitor what goes on in the sun? Because if we can't get a little bit closer, it's darn hard and really hard. So in about 2018, the Parker probe was sent, took a couple of 3 years to get there or actually get positioned, and it tries to monitor the outer layer and the magnetic fields, and as they get away from the sun before they actually move on and on and on. And it came as close as a couple of million miles from the sun itself. And we are indebted to people who at Johns Hopkins and other universities that created the heat shields for these, so at least it can be there instead of just vaporizing in a very fraction of a minute. And it started taking data in about 2021. again, we're lucky to be living these days because next month, NASA is scheduled to send the next probe, not to the sun, but the most advanced probes, 4 of them, to right outside the Earth, which combine optically called the Punch Project. But 4 of them are able to look at the sun in a wider angle mode, and hopefully from close to Earth, actually. It get better data on how this, not just what comes at you, but how does it really look from different angles. And they're hoping that that will open up many answers to these very complicated questions. All right. So again, right now, what satellites monitor on a daily basis? These are called GOES satellites, the first of whom was launched in 1975. Now we get data from GOES number 16 and number 18. This stands for Geostationary Operational Environmental Satellite, which means that these satellites are right above your head. They remain in the spot 22,000 miles up from us at the same spot unless you want to move them. And they measure the electrons, protons, and the magnetic field. So how does it affect our lives on Earth? We got a couple of slides coming up. In about 1989, I think it was, where Quebec and back into the northern part of the United States, New York State, almost lost a lot of electric power because that's why we monitor them. One of the reasons we do, because magnetic fields, as you say, current creates a magnetic field. The funny part is the magnetic field creates a current. So if your transformers are exposed to such a high magnetic field or intense magnetic field, and so the Earth's magnetic field was not able to cancel them out, literally you induce electricity in something which doesn't need it, and it burns. The GPS system is sensitive to that. The positioning system, your airplanes are run based on that. They have to constantly adjust if the magnetic things change. HF radio is a branch of radio communication which bounces off the ionosphere. You want the ionosphere outside the Earth to talk to far, far, far away, anywhere virtually on the Earth, depending on the circumstances. Satellites are highly exposed to electromagnetic radiation, all the way from X-rays to gamma rays and so on. And they want to know. They want to know when the solar flares are highly intense. They need to know. These are expensive pieces of equipment, and losing them is not a good thing. Now here comes something not so obvious, the drag. These satellites are actual solids, and the space is relatively empty, but not empty. They experience actually forces, so when these particles come in, these satellites are harder to actually position. Very interesting. Here you have on February 21st and 22nd, I believe it was last year or the year before, AT&T actually had high interruptions of the telecom system, which was actually linked to just that. Now here, look on this again goes back to the Quebec issue in 1989, March 1989. Look on the right-hand side. And that used to be these transformers are bright wires. They got coatings on them. They look real fancy. Look at the picture on the right. It looks as if something was put in the volcano and dished back out. That is not a wire that is happy. Yeah. And this was the result of that time. So what do we monitor at all time? The corona, the outer layer, the mass ejection, the ionosphere right outside Earth, the solar storms, and the sunspots, which might originate. And look at the beautiful results of that if you're lucky enough to live at high latitudes on Earth. You see on the right side here, you see the northern lights or the southern lights, which are the interaction of actually taking place when the magnetic fields interact with the particles, the electrons and protons from the sun interact with Earth's magnetic field, and look what you see. Here we do one of the things that we monitor is kind of cool, called the K factor, again by the same people. Yeah. In other words, this is not just, they monitor many things, the magnetic field, they monitor the electrons, they monitor the protons, positive, negative charges as they blast us. But here's like the bottom line. How does right outside the Earth, right outside, what is happening here that's protecting us? Again, the title of today's talk is Sun and Us. So that's why I'm picking that bit of information out of the vast amount of information that is available to you on this website 24 hours a day. So there you go. And so what you see is how intense it is outside. How much is it protecting us? Where are the weak points? Where are the strong points? They monitor that every 3 hours for us. Here is a sample of a solar telescope. Again, I do not recommend looking at the sun. It's by the naked eye, or even they make some stuff that supposedly will protect your eyes, but I prefer that you step it up one notch and just do it safe. Again, now how we come back, now we were all the way out there, millions and millions of miles away. Now we settle down slowly and we come back to what supposedly our reality is, which is our air, our water, and our food. And here's a typical thing what happens. This is for the biologists in attendance. The beautiful photosynthesis, aerobic photosynthesis, where water comes in, carbon dioxide is absorbed, oxygen is emitted, and the food necessary for the plant is also generated. And here we are now allowing us for light to come, heat us up, make the water be liquid, give us food, and wow, us. Let's move on. So what I like to do at this point in time, we are just about, I believe, at 11:18, just enough time for a few minutes of questions. I really appreciate you being here today and everyone involved at this time. Mr. Brad is kind enough to now share that with us. Thank you. And also, Ms. Galanis, I really appreciate her hospitality today, the library system as a whole, which has done me so much good over the years. I'm indebted to that system as a whole.
Thank you so much, Dr. Pashaie. I've got a question, and this is going back to my high school science classes. What are the Van Allen radiation belts? Are they interacting with the sun?
Those are actually named after the gentleman by the name of Van Allen. I think it was almost the University of Iowa, if I'm not mistaken. So those are the bells that actually surround the closure of this constant magnetic field that are around us. I can look it up directly how it's actually defined, but those are named after a gentleman, really famous gentleman, but those are in fact magnetic fields by a gentleman by the name of Van Allen.
I didn't remember if they came from the sun or if they were somehow.
Let me just give you a really correct, quick answer. That is how it's officially actually. There we go. So we go. Really, yeah, they've been known for a few years now. James Van Allen. Yeah, James Van Allen, American space physicist, Van Allen belts, and it says, let's see how it is officially. This is how they say it. Van Allen radiation belts is a zone of energetic charged particles, like we're discussing today. Most of it originate from the solar wind that are captured and held around. Guess what? That originate from the and are captured and held around the planet by that planet's magnetosphere, which is right outside us that we were discussing. Yeah, again, 1958, according to my phone, James Van Allen. Yeah, and his association was University of Iowa, space physicist, and developed the instruments they basically to be able to measure the magnetosphere outside Earth. Yeah? Thank you.
And I just read earlier today that they're expecting the aurora tonight if you live in Northern Europe or Northern Canada.
Yes,
so
yes.
I know it's on my bucket list to see the aurora.
Yeah.
So
maybe you can get a YouTube, or there's some people who actually put that on YouTube. The funniest thing is that these things actually make noise. If you can able to detect it, they sound, if you have a detector, very low frequency, they go, go on, go find the YouTube. It's kind of cool, actually. Yeah.
wow, I've heard the music of the spheres, but I didn't know it was more like wind.
You can't hear them, but if you do it right, you can. If you have a transducer, a sensor, you can hear them.
Dr.
Any
Pashaie,
other questions for Dr. Pashaie in the chat? Or
yes, there's one in the chat that says, does the 11-year cycle mean we'll be seeing even more of the northern lights as far south as Missouri?
Yes, the flares, basically these storms, these flares which create the storm outside us become very intense. Yeah. So the question is really a good one, because then you're really concerned about where the weak spots are and where the strong spots are. That's why people travel up there in Fairbanks, Alaska, and close by to see how the changes are as a result of that. So yes, the stronger those storms are, the more you're going to see, because the more energetic the particles are. And then refer back to the map. Here you are. There's Fairbanks somewhere out here, and it's black. Here's the Earth's magnetic field coming in like this around the Earth, and suddenly the particles come along that line now, but they're going like this. Electric back there, they go boom, 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 bam. They blast the Earth's ionosphere, and they energize that. So in part they protect us, in part they try to attack us. It's a give and take. Yeah. So yes, the answer is yes.
what causes the colors of the aurora? Is it the different gases?
Oh yes, yes. That I believe, I'm going to double check that. I believe it all has to do with a lot of things, because the ionosphere has different layers. The energy what comes in have different energies. So remember, these are photons being emitted. So in order for photon to be emitted, you have to have some energy, okay? It has to relax, and the relaxation of that energy emits a photon. Now, so the energy and the energy of the photon emitted must be less than the energy you originally had. So the more energy you got at the beginning, the more bluish you have a chance to get. Now that gets a little complicated because these are different elevations from the Earth. It gets a little complex, but the fact remains it is related. That is, the more energy you got, the better chance you got to get the purple ones. And I'll be more than happy to forward a complete article, because I have to do it justice, and I cannot do it in a couple of minutes. People spend a lifetime doing this. So yes, I appreciate the question. And again, the answer is yes.
Any other questions from our audience? Hey, Dr. Pashaie, thank you so much for your presentation. We all learned a lot about the sun, and I'll think about it as I walk across campus today and feel the sun's rays and think what's coming at me. So thank you once again.
Yeah, it's been a pleasure, as always. And I'd like to thank everyone in attendance, and also the college, Brad here, and then Ms. Galanis, and the staff, and the dean, and the president that made all of this a possibility. Yeah. Have a very peaceful weekend and a healthy one. And I thank you.
Thank you again, Dr. Pashaie.